Now we'll look at our last two convergence tests, and this will complete the study of the 9 different convergence tests that I asked the students to know for BC Calculus. There is one more test, and it's in your book, and it's called the root test. I normally make that a bonus question, but of course this year is different. The first comparison test is called direct comparison. You've already learned this idea. It's exactly the same as with improper integrals. Here are 2 examples. You may want to pause the video and figure out the convergence or divergence of these 2 series. And that's the question we're asking. We're not asking you to find a sum. Just give you these 2 series and ask you, do they converge or do they diverge? Show your work. That's the kind of thing. All right, now look at this first one. This one here, because this denominator is bigger than n to the 4th, then that means this entire series is smaller than this series. Smaller than that p series. This one, because we've already learned about p series, we know that has p larger than 1. Therefore, this one converges. So this is a series that's smaller than a converging series. Therefore, this original series converges. Do the same idea with this one. And notice I had to start at n equals 5 because I don't want to divide by 0 problem. All right, this one is clearly bigger than what common series? Well, we would do this, 1 over n. Clearly bigger than that, that's a p series with p equals 1. Therefore, this one diverges. This is larger than a diverging series. Therefore, this one diverges. So you've already seen this idea with improper integrals, so we won't go through any more details than we did back then. Here's the rule, the test. If a series is smaller than a converging series, then that series does what? Then that original series converges. And if a series is larger than a diverging series, then that series diverges. What if it's one of the other 2 possibilities out of 4? What if a series is larger than a converging series? What does that tell you? What if a series is smaller than a diverging series? What does that tell you? And the answer is it tells you absolutely nothing. Right? That was the first of the 2 comparison tests, the direct comparison test, easier to understand. This one's a little trickier. I teach this in 2 approaches. First is the loose definition, the one that helps you do a problem quickly. The second is the strict definition, the strict terms of this test, the theory, and this is in your book, and I'm not going to cover that this year. You really don't have to know it to do any problem. It might come up in the homework, and if it does, you can check in your book or ask me a question. But this year, we will skip the strict definition of this and look only at the loose one. And we also mentioned this when we did improper integrals, and that's the idea of looking to see what family a series is in. Now, I'm going to skip right ahead to the example so I can talk about that. Not everything falls into a family. That's not automatic. It's only if you have the original function of the series be some kind of fraction. And when you simplify it, as n gets bigger and bigger and bigger, so that you keep the largest term on top and the largest term on the bottom, like that, if that then simplifies into a p series, then we can use this idea and we can use the concept of the family that it's in. And you'll see on the next board that that doesn't always work. That's not always a thing you can do. So here's loosely what the limit comparison test tells you. If you have a series of the form of a fraction, you keep the dominant term on top and the dominant term on the bottom. That is the one with the largest exponent on top and bottom. If you do that and you get a p series, then your series does the same thing as that p series. It's in that family. You can identify what family it's in, and all the members of that family do the same thing. They either all converge or they all diverge. All right, so let's look at our 2 examples. Here we keep since n's getting bigger and bigger and bigger, those are the terms we care about, right? The terms that go on and on, so-called forever. Keep the largest term, that's going to dominate on top. The largest term here, the largest exponent, that's going to dominate on the bottom. The rest will be insignificant as n gets bigger and bigger and bigger. You can always put any coefficients out front. They don't matter. They don't affect convergence or divergence. So look what remains. N over n cubed. Simplify that. 1 over n squared. That's the family that your series is in. The 1 over n squared family, this is a p series with p equals 2, which is greater than 1. Therefore, this original series converges. And that's all you have to do. You don't have to do anything more fancy than that. You just use the algebraic simplification tools, basically. The simplification tools you learned last year in AB when you have the variable getting bigger and bigger and bigger and you keep the most dominant term on the top and bottom, and then you simplify. Okay? Do the same thing over here, and you can pause the video. Right? Largest term on top, ignore the rest. Largest term on the bottom, ignore the rest. Don't worry about whether it's a fraction or not. 3/2 is still larger than 1/2. It always works no matter what they are, whether they're fractions, whether they're smaller than 1, greater than 1. The concept always works. So you get n over n to the 3/2. And what family is this in? It simplifies to 1 over n to the 1/2. Again, this is a p series. This time p is smaller than 1. Therefore, so it's in this family, which is a diverging series family. Therefore, your original series diverges. Okay? No need to do anything fancier than that. No need. It looks very complicated at first, but you identify which family it's in because then it's getting bigger and bigger and bigger. Right, now at this point, you might have a question. This seems so simple. Why don't we just always do this? Why do we even have to think of direct? Why not always do limit comparison? Why would you ever do direct comparison? Why would you hunt for some series here to compare it to when you can just identify which family it's in? Well, think of the restriction we put on limit comparison and you'll get the answer to that question. Why would you ever need direct comparison? Because not all series fall into a p-series family. In other words, a 1 over n to the p family. Now, it's possible to identify other types of families, geometric series family and so forth, but this is the only one you have to know in our class. They're exponential families. You could identify a lot of different types of families. The log family in particular can be useful to understand, but that's not part of this course. This is the only type you need to know for our class. All right, here are two examples of ones that don't fall into a simple p-series family. Look at this one. You can pause the video if you want to try these and think about them. This one in particular can be pretty tricky at first because you're trying to find some kind of similar function, but that's not the way to think about comparison, to try to look at the whole thing and think of a similar function. Rather, think about the top and the bottom. And look, the bottom is giving you a big clue. 1 over the square root of n. Okay, and that, if we put a 1 on top, that would be a p-series, and we can answer the question very simply about convergence or divergence. So let's put a 1 on top and see what happens. Okay, the bottoms are the same, so they don't affect the comparison. But look at the top. As n gets bigger and bigger and bigger, which of these two is larger? Log of n or 1? And see, you can compare a function to a constant. That's okay. So once you think of it that way, and I think a lot of people, including myself, they kind of have to see this once to get the idea. I don't think I came up with this on my own when I first learned it. I had to see it, and then light bulb went off. I said, oh, aha, okay. I will keep that in mind from now on. Right, so you get this. We're going to put the series symbol there. Right, so since log of n is bigger than 1 past a certain point, right, even though log of certain numbers will create something smaller than 1, we're not worried about that. We're only worrying about as n gets bigger. Right? That's what determines whether something converges or diverges. So n increases, log of n gets bigger than 1, and so this inequality holds. What does this series do? This series diverges because p is less than 1, therefore this series diverges. Right? Now let's look at this one. Now you look at this and you might think, well, I could just do the ratio test. It's a factorial. I can do the ratio test. And that's true, but think about how long that test takes and how likely you are to make, how likely I would be to make a mistake. You may also look at this and think, well, it just feels like it should converge. Factorial is the fastest increasing function. I know that if I put exponential there, it will converge. So I'll bet this converges, and that's true. And that would actually get you the right answer, and there's nothing wrong with that thinking. But if you were asked, if you were required to use comparison here, direct comparison, you think, what could you compare it to? If you put a little thought into it, look at 1 over 1, 1 over 2 times 1, 1 over 3 times 2 times 1, 1 over 4 times 3 times 2. Look at that, that's 4 times 6. pretty quickly you can convince yourself that past a certain point, not immediately, but past a certain point, every term is always smaller than the corresponding term in that series, right? Not here, not here, right? This is not 1/2 is not smaller than 1 over 2 squared. This is not smaller than 1 over 3 squared, but this is smaller than 1 over 4 squared, right? 1 over 4 squared would be 1 over 4 times 4. This is 1 over 4 times 6. And if you look at successive terms, you'll see that will always hold. So it's pretty easy to convince yourself of this. So if you're asked to prove that this converges, this is the fastest way, a direct comparison to 1 over n squared. And it turns out because of growth rates, you could have put 1 over n cubed here, 1 over n to the 10th, 1 over n to the millionth. Eventually, 1 over n factorial will be smaller than 1 over n to the anything. All right, since we know this series converges, and this is smaller than a converger, therefore this series converges.